Hey, welcome back. With 3n+1, all numbers seem to go down to 1. With 5n+1, on the other hand, lots of numbers seem to run off to infinity. Well, there's 3 known 5n+1 loops. But for any other number, well, it could get sucked into one of these loops, like 66 goes to 33, or the number runs off to infinity. For example, 7 goes to 18, 9, 23, up to 19 million pretty quickly, and it doesn't ever seem to come back. Now, of the first 100 numbers, 40% get sucked into one of these loops. But of the first 1,000 numbers, only 17% get sucked into a loop. And when we look at the first 100,000 numbers, only 3%. So since this percentage gets lower and lower, we conjecture that in the 5n+1 problem, almost no numbers get stuck in loops. So why the difference between 3n+1 and 5n+1? Well, if we assume a sequence has just as many odds as evens, which is a big assumption, then after 2 steps, n becomes about 3/2 n times half, so that's 3/4 n. So we expect 3n+1 trajectories to trend downwards. However, with after 2 steps of 5n+1, we're more likely to be at 5/4 n. So with more steps, we expect a 5n+1 trajectory to grow to infinity. In this episode, we're going to take it up a notch, and it's going to get a lot more interesting. So instead of a two-way rule, let's look at a multi-way rule like this one. We start with n. If n's divisible by 3, we double it and then divide by 3. If there's a remainder of 1 when we divide n by 3, we multiply by 4 and subtract 1, then divide by 3. Otherwise, multiply by 4 and add 1, then divide by 3. So for example, 7 has a remainder of 1 when you divide by 3, so it goes to 4 times 7 minus 1 over 3, which is 9. Now, this isn't just some weird format. In fact, it's easy to write the original 3n+1 problem in this format. So if n is divisible by 2, we multiply n by 1 and divide by 2. Otherwise, we multiply n by 3, add 1, and divide by 2. So now let's ask, how about this three-way rule? Will most numbers run off to infinity, like 5n+1? Or will most numbers eventually get snared by a loop, like 3n+1? Well, if we assume a sequence contains all 3 kinds of numbers in equal amounts, then after 3 steps, we'll have multiplied a number by 2, then 4, then 4, so we'll be 32 times higher. But at the same time, we'll have divided it by 3, then 3, then 3, so we'll be 27 times lower. Since 32 is bigger than 27, we expect most sequences to trend upwards over time. That's called the Matthews-Watts Conjecture. It's a more general version of the 3n+1 conjecture. If the product of these coefficients is greater than the denominator to the denominator, they call the rule expanding. Otherwise, they call the rule contracting. The conjecture is that with expanding rules, almost all start numbers diverge to infinity, but with contracting rules, all start numbers get snared into some loop. In this example, even though most numbers for the rule seem to head off to infinity, there are a lot more cycles waiting to snare unsuspecting numbers. For example, there's this cycle involving 99. So if you're a start number like 22 and you're ready to head off to infinity, well, right away you get cut in half and you're part of this loop. So sorry, 222. Now the most stressful rule will be one that's barely contracting, like this one. Here, 1 times 3 times 5 times 17 is just shy of 4 to the 4th. Still, the conjecture says that all numbers get snared into a loop. And sure enough, no matter what number you try, you wind up in a loop, just like 3n+1. Here, 23, you can see, tries to pull away, but eventually falls back into the loop of 10 and 13. It's sort of like how 27 tries to escape in the 3n+1 problem, but it can't. Now finally, here's an example of a barely expanding rule. So this one's specifically designed so that 1 times 2 times 3 times 521 is just a tiny, tiny bit bigger than 5 to the 5th. Anyway, since this is a barely expanding rule, we expect all start numbers, almost all start numbers, to diverge to infinity. but we also expect a lot of crazy loops waiting to snare unwitting victims. So let's try start number 3. That's a really simple number. So it goes up and looks like it's diverging to infinity as expected from this expanding rule. Here it's pushing 14 billion. Should we keep going? Yeah, let's keep going. All the way back to 3, and it's actually part of a loop. I think there's a moral lesson here somewhere for us humans. Or look at 43. You can see the pull downward is about the same as the pull upward, and it happens to wind up at 1, like a gambler in Las Vegas, just out of money. Now, in fact, of the first 100 start numbers, 91% of them get snared into some loop. So does that mean the Matthews-Watts conjecture is wrong? This is supposed to be an expanding rule. Well, of the first 1,000 numbers, only 86% get stuck in a loop, and of the first 100,000 numbers, only 83% get stuck. So this percentage is also going down. And that means even though most human-sized numbers do get stuck in loops, once we get out to these massive inhuman numbers, we believe almost all of them are going to be big enough to avoid these little traps. That's what the conjecture says anyway. All right, see you next time.